Let's start by remembering what we learned about the connections between a function and its first derivative. So, some of the things we remembered, if you have a positive derivative, the derivative is positive, that means it's increasing, negative, decreasing, and so forth. So looking at this polynomial, at what values of x does g of x have a relative maximum or a relative minimum? So we see the points. There's a max and there's a min. So we would say x equals 0 is a relative max and x equals 2 is a relative minimum. What does that mean about g prime at those values? So g prime of x equals 0 because a horizontal tangent line can be drawn at x equals 0 and x equals 2. If we look at this function, though, do we have relative maximum and minimum? Well, we have this point, which is technically a minimum. So at x equals -1, that is a relative, is a relative minimum. Now, what can be said about f prime at that value? Well, at that value, f prime of x is not going to be 0. That's a sharp turn. That's a cusp. F prime of x is undefined at x equals -1 because there is a cusp or a sharp turn. So we're adding that feature in, that it's not always that a max or min occurs when the derivative is 0. Sometimes it actually occurs when it's undefined as well. So let's look at it algebraically for f. So f of x was x plus 1 to the 2/3 plus 2. If we take the derivative, we're going to have 2/3 times x plus 1, subtract 1, times the derivative of the inside, which is just a 1, and then plus 0, which that's really 2/3 times 1 over x plus 1 to the positive 1/3, which would be the same thing as the cube root. So 2 times 1 is 2, 3 cube roots of x plus 1. Now, when you have a fraction, to know when that's going to be 0, you look at the numerator. So in this, f prime of x will never be 0 because, well, 2 is not 0. F prime is undefined when the denominator is 0. And that's only going to happen when x is -1. So let's do a sign analysis. We know what's happening graphically, but let's look at our sign chart. So at -1, f prime is undefined there. Let's pick an x value to the left and to the right. I'm going to pick x equals 0. So if I plug that into my derivative, I've got a positive number on top, and the cube root of 1, that's going to be positive times that would be positive. If I pick a number over here, let's pick x equals -3. 2 still positive. When I plug that in, I get negative, and the cube root of a negative number is still negative, so the denominator will be negative. So I end up with a negative number on this side and a positive number on that side. So does that match what was in the graph? The derivative is negative, going up to -1, and then it's positive. So notice we still have that change from negative to positive. So f prime is negative on the interval of -∞ to -1. So f of x is decreasing on that interval. And it matches the graph. F prime is positive on the interval from -1 to +∞, and that does portray that f of x is increasing on that interval. And f prime still changes from negative to positive at x equals -1. So there is a minimum. And that does match. So the basic rule of that f prime is 0 at every max and min isn't always true. But the fact that it changes from negative to positive is what we want to make sure we look at. So we're going to kind of clarify some things that we had done before. So critical numbers are anywhere where we have this change. So critical numbers are a value of x where a function's derivative is equal to 0 or is undefined. Critical points are when you're going to have a potential max or min. So anytime we know the derivative is 0 or undefined, at that point this has a potential relative maximum or minimum. If f prime is greater than 0, then the function is increasing. If f prime is less than 0, the function is decreasing. If f prime changes from positive to negative, then we definitely have a relative maximum. If f prime changes from negative to positive, then we have a relative minimum. So this is all the things that the first derivative can tell us about. So we're also going to be adding the second derivative. And it talks not about increasing and decreasing, but about something called concavity. A function can be concave up, concave down, or have what is called a point of inflection. So let's look at G, which we looked at earlier. Hopefully in advanced math, pre-cal, you talked about points of inflection. Point of inflection is where the graph changes concavity. Changes which way it's opening. So we can notice that on this graph, it's opening down, concave down, and then it becomes concave up. And it looks like it happens halfway between those two maximas. So between the maximum and the minimum, and it does. Looks like it's about there. So we would say that g of x appears to be concave down on the interval from negative infinity to 1, and g of x appears to be concave up on the interval from 1 to infinity, with a point of inflection at approximately 1, negative 2. Well, all this appears and approximately, that's not really what we like to do in math, right? We want to be exact. We want to find those points. So how do we do that? How do we make sure that's where the concavity changes? Well, what we're going to do is find the second derivative of g. So g of x was, let me write it down, it was x cubed minus 3x squared, and the first derivative would be 3x squared minus 6x. So the second derivative just means to take it again. That's going to be 6x minus 6. We'd like to figure out where g double prime changes signs. So let's find when it equals 0. Well, that's going to be when 6x equals 6 or when x equals 1. So I'm going to make a sign chart. This time, so here's our 1, that's when we change signs. This is going to be for g double prime. So we need to pick a value from left side and from the right side. So if I pick a value from the left, I'll pick 0. And if I plug it into g double prime, what do I get? let's see, 6 times 0 minus 6 is going to be negative. If I pick, let's say, 2, that's 12 minus 6. It's going to be a positive number. So what g double prime tells us is that g of x is concave down on the interval from negative infinity to 1 because g double prime is less than 0. G of x is concave up on 1 to infinity because g double prime is positive. We also can tell from this sign chart that there's a point of inflection at x equals 1 because g double prime changes signs. Oh, I ran out of room. So let's recap about the second derivative. So the second derivative, when it's 0 or undefined even, the original function has a potential point of inflection. When the second derivative is positive, we are going to be concave up. That means the graph is going to open up. If it's negative, the graph is concave down. When the second derivative changes signs, positive to negative or negative to positive, either one of these tell me that it has a point of inflection. Concavity changes. So let's try a couple. We're going to find the x values for points of inflection and talk about the concavity of the function. So the first thing we need to do is find the second derivative. So start by finding the first. First derivative is going to be 4x cubed minus 12x squared. The second derivative, just do it again. 12x squared minus 24x. Now to figure out where our potential points of concavity are, we're going to need to set that equal to 0 to find those critical points for our second derivative. So I think I can factor out something. I think they both have a 12 and an x. If I factor out 12x, I'm going to have x minus 2 equals 0. So this happens when x is 0 or at x equals 2. So let's make a sign chart for f double prime. And my points of interest are the 0 value and 2. So I need to pick a point to the left of 0. How about -1? Now I'm plugging it back into this factored version because it's so much easier. If I plug -1 into this first factor, it's going to be a negative number. And -1 minus 2, that's going to be a negative number. So overall, it's going to be positive. If I let's pick 1. 12 times 1 is positive. 1 minus 2 is negative. So in this realm, the second derivative is negative. After 2, 3 sounds good. We'll have positive and positive. So overall, it's positive. So what does this tell me? Well, it tells me a lot about concavity. So we are concave. Oh, I should say f of x is concave up on from -infinity to 0, and then from 2 to infinity. Why? Because f double prime is positive. F of x is concave down on the interval of 0 to 2. Why? Because f double prime is negative. And then f of x has points of inflection at x equals 0 and x equals 2 because f double prime changes signs. Next example. Ooh, we get to review product rule. So this is made up of 2x and e to the x. So, first time through. F prime. We're going to take the derivative of the first times e to the x, just like it is. Oops. And then we're going to have plus the first times the derivative of the second, which is going to be e to the x, times the derivative of the exponent, which is just a 1. Clean that up a little bit. F prime is 2 e to the x plus 2x e to the x. Now I want to take the second derivative. The derivative of 2 e to the x is going to be 2 e to the x. Oh, 2x e to the x is what we just had. So plus 2 e to the x plus 2x e to the x. Now if I pretty that up a little bit, I have 2 e to the x plus another one. That's 4 e to the x plus 2x e to the x. And I want to know when that equals 0. I think there's something I can factor out. They both have a 2, and they both have e to the x. That leaves me with 2 plus x. So if I set each of my factors equal to 0, oh, that one's going to give me -2. That's easy. This is never actually going to be 0. So it's of no concern to mine, because e to the x, there is nothing I can put in that exponent that gives me 0. Ever, ever, ever. Now let's do a sign chart. So the only x value I'm concerned with is -2. Let me pick, say, -3. If I plug -3 in, that's just going to give me a fraction. So it's still going to be positive. And 2 plus a -3 is going to be negative. So overall that's negative. Something bigger than -2, 0 sounds good. E to the 0 is just 1, so that's going to be positive. 2 plus 0 is going to be positive, so this is positive. So for this one, f of x is concave up when we're positive, so from -2 to infinity, because f double prime is positive. F of x is concave down in this area, so from -infinity to -2, because f double prime is negative. And f of x has a point of inflection at x equals -2, because f double prime changes signs. I have another example. Which is going to be a good review of Quotient Rule. Yay! Okay, so, oh, they already gave us the first derivative. How nice of them. So we just need to find the second derivative. So the derivative of the numerator is 0 times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Let's see, I can pretty that up. That's going to be 0. That's going to be a -6x equals over x squared minus 3 squared. Now when we have a fraction, we have two things we need to look at. We need to figure out when f double prime is 0. We also need to look at when it could be undefined. So let's look at each of those cases. F double prime is 0 when the numerator is 0. Well, that only happens when x equals 0. The denominator would be 0. Gives us undefined. So square root of 0 is still just 0. That gives me x squared equals 3. So x equals plus or minus the square root of 3. So I've got 3 points of interest here. So on my line chart, I need to go to negative square root of 3, 0, and positive square root of 3. So if I pick a number over here, I don't know, let's go with -3. That sounds good. Negative times a negative is going to be a positive in the numerator. Negative 3 squared. Oh, doesn't matter what I get in the middle, huh? If I square it, it's going to be positive. So overall, this area is going to be positive. Something between that, x equals -1, sounds good. I'm going to have positive over a positive, which is positive. Let's see, between 0 and square root of 3, let's go with x equals +1. It's going to be a negative in the numerator. Here, let me circle these just so that they don't get in the way. When I plug 1 into the denominator, it's going to be positive. So that's going to be negative. X equals, I don't care, 5. Negative in the numerator, positive in the denominator. So notice what happened on this one. We can talk about our concavity and then start thinking about where the points of inflection would be. So f of x is concave up on negative infinity to negative square root of 3, and then from negative square root of 3 to 0. You could include the whole thing if you wanted to. But technically that's where it's undefined, so something weird's happening there. So I would leave these as two separate pieces. And why is that, being concave up? Well, that's because that's when f double prime is positive. F of x is concave down on 0 to square root of 3, and then from square root of 3 to infinity, because f double prime is negative. And our point of inflection is when we change concavity. F of x has a point of inflection at x equals 0 because the second derivative changes signs. It does not change signs at negative square root of 3 or at positive square root of 3. There's something else neat that we can do with the second derivative. It can also help us with our maxes and mins. Alright, so remember that we know if f prime of x is 0 or undefined, we have a potential relative max or min. So let's say we already know that f prime of x is 0 or undefined. Well, what if it's 0 or undefined and f double prime at that point is less than 0? So we're concave down. What is that going to mean? So, concave down and a possible horizontal tangent means that we have a relative maximum. What if, okay, so we already know first derivative is 0 or undefined. Second derivative is positive. That means we're concave up. Concave up. Relative minimum. What if first derivative is 0 or undefined, and then the second derivative is 0 or undefined? Can you make a conclusion? No, no conclusion. That's not enough to know anything. If both of them are 0, I don't know what's going on there. Could be just a point of inflection. I don't know enough. So I want to at least do one example of that. So using the second derivative to test a point to see if it's possible, possibly a max or min. So first we need to take the first derivative. We need to find our critical points. That means I need to take that and set it equal to 0. I think I can factor out 4x squared and have x minus 3. So my critical points are x equals 0 and x equals 3. Now, let's take the second derivative. So second derivative would be 12x squared minus 24x. What happens if I plug in zero? I get 0. This means x equals 0 is not guaranteed to be a relative max or min. Let's try the next one. 3. F double prime of 3 needs to plug 3 in. So 12 times 3 squared minus 24 times 3. Well, that's going to be positive. So that means f of x is, so it's positive, that's concave up, is concave up, which makes x equals 3 a relative maximum. Oh, let's go ahead and do the last one. Oh, especially because you love doing trig functions so much. First derivative. Derivative of cosine is negative sine, so it's going to be negative 2 sine theta minus 1. I'm trying to find my critical points. I'm going to set that equal to 0. Negative 2 sine theta equals 1. So sine theta equals, divide by negative 2, you get negative 1/2. And negative 1/2 is going to be in the bottom quadrant. That's going to happen when theta is, so 1/2 would be at pi over 6, so that makes it at 7 pi over 6 and 11 pi over 6. to use the second derivative test, I need to take the second derivative. So the derivative of sine is cosine, so that would be negative 2 cosine theta, and that's it. Now for this second derivative test, you're just figuring out if these are maxes or mins, so you're just going to plug them in to your second derivative. So that's negative 2 cosine of 7 pi over 6. Now remember, we're just looking to see if this is negative or positive. Well, 7 pi over 6, unit circle, is over here. So both cosine and sine are negative there. So this is really going to be negative 2 times a negative number, which is going to be positive. Therefore, f of x is positive, is concave up. So theta equals 7 pi over 6 is if it's concave up, that would be a relative minimum. Plug in 11 pi over 6. Well, 11 pi over 6 is going to be over here, and cosine is positive in that quadrant. So my answer is going to be a negative number. Therefore, f of x is concave down. So theta equals 11 pi over 6 is a relative max. And there's some problems where you can try these.